And thank you so much. Thank you to AIT for inviting me, AIT Solutions, and in particular, thank you to Dr. Anwar for inviting me to come and address you this afternoon. What I want to share with you is a bit of history over the last 25 years and lead you quickly to where we are today. I started working on performance-based seismic design, actually unknowingly, when I was a graduate student at UC Berkeley. One of my professors at UC Berkeley was a very famous professor named Professor Bertero. And he taught a class then called Limit States Design. And this is really the precursor to what we know today as performance-based design. And so the idea there of limit states design, of course, is you design a building and then interrogate its performance against certain acceptance criteria, against certain limits, whether it be strength or deflection or rotation or what have you, and then you assess how that building performs against that criteria. And you can use that for all sorts of input demands, whether it be seismic or wind or natural events like blast or what have you. And so this kind of had its roots in Professor Bertero's class. 10 or 15 years later, we started doing something that's called displacement-based design, and this was the precursor to performance-based design. And it wasn't until about 1995 that we actually started doing what today we call performance-based design. And for the last 22 years, myself and my colleagues in my firm, we've been advancing and developing this approach to seismic engineering. And so I want to share a bit with the lessons learned, the history, and kind of how we got to where we are today, in hopes that it may help you. The number one thing that I'll share with you today is I've been doing this performance-based design for 22 years, and on each project I've learned something new. It's not a static process, it's not a static procedure. We're advancing it and making it better and learning things on each and every project. So when you look at the guidelines or any documents out there, papers that were written by myself or others, guidelines from San Francisco or Los Angeles or Japan or Korea or wherever, you should know that those are not static documents. Those are snapshots in time as to what we are thinking today. And know that tomorrow it will change. Right. So let's see if this will work. So, seismic design in the world, and in particular, most of my reference will come from the west coast of the United States, started in its infancy in the 1920s. This is 1920s Los Angeles. But of course, today in Los Angeles, it looks very different. And so the thinking that started in the world of seismic engineering in the 1920s is not all that relevant to the buildings that we're building today. Seismic engineering really started to take off and developed its fundamental premises in the 1940s and 1950s. This is San Francisco in the late 40s. And it was in the 40s and 50s that the underlying philosophies of seismic design were created. And those philosophies that we'll talk about still hold true, meaning under different levels of demand, we should expect different levels of performance. And what are those targets? That's the underpinning of the philosophy. But then, as you know, as you recognize, the tools that were available to engineers in the 1940s and 50s were very, very different than the tools we have today. Then they didn't even have a simple calculator. Things were done with a slide rule and a pencil and a paper. No computers. And so the methods that were required in order to facilitate design of buildings that we know today were very different then. And so the methodologies that were used need to be simplified. So we'll talk about that a little bit. In every country, right, there's some code which serves as the basis of design for the safety of buildings. In the US, we use the IBC, which has its underpinnings in a document called ASCE 7, which many of you probably are familiar with. But embedded in those codes is this basic premise of there's an earthquake, some demand level, and associated with that demand level, there's a performance. And so in the US, these are a pretty classical diagram where under certain levels of earthquake, we want to have certain levels of performance. This particular graph is really the fundamental premise of the building code. It talks about under a frequent earthquake, and in the US many times we define this as an earthquake that has a 50% chance of exceedance in 30 or 40 years. It turns out to be about a 42-year interval. And then we look at the different performance levels, whether it be operational or immediate and so on. Anyway, the point being here is that there's different levels of earthquake and different performance objectives that you might target. And this is a framework that was established actually back in the 1940s and 1950s, but there wasn't a methodology then to specifically allow engineers to assess each of those targets. It had to be simplified. And so, this is a little bit late, but I think you all understand. Everybody here, I think, is an engineer in the room. So this dashed line here is a 500-year response spectrum for an earthquake. And the idea embedded in the code is, given that earthquake, given this 500-year earthquake, so you have acceleration and you have building period, given that 500-year earthquake, we want the building to be safe. But it's recognized that under that earthquake, there'll be some nonlinear response of the building. And in the 1940s and 1950s, there was not the ability, there wasn't the computational ability to easily calculate and assess that nonlinear response. So what did they do? They came up with this magical factor. In these days, we call R. Before R, it was R sub W, and before R sub W, it was K. But basically what it was is takes the design earthquake and divides by a number, somewhere between 3 and 8. And that number is somewhat reflecting of the ability of the system to respond ductily, to respond non-linearly to the earthquake, reducing the forces so it allowed the engineers then to do a simple elastic analysis and simplified hand calculations. So, the point being there that the R factor, when it was created, then the K factor, was not a product of lots of scientific study or testing or computer modeling. The R factor, number one, was the result of a committee negotiation. It was a compromise number, and it was a number of convenience. It allowed the engineers to actually do their work when otherwise they wouldn't be able to do their work. So it was a tool that was used then to take a very complex problem and simplify it. Today, of course, we have much more powerful computational tools at our fingertips, and so we don't really need this crutch, if you will. We don't need this simplified tool, and embedded in that R factor, right, is a lot of assumptions that may or may not be true for any particular building. All right, so of course, in Thailand, in Bangkok, the seismicity here, as you all know, is quite low. Although we were talking over lunch today that the basin effects that may be present here in Bangkok could be substantial for long-period structures. The rupturing fault may be a great distance away, but as those waves travel through the Earth's surface and they reach Bangkok because of the soft soils that are present here, those will be amplified, and perhaps larger buildings may in fact be more prone to being hit by the earthquake. Other places that we work, though, this is Manila. Of course, the Philippines is very, very seismically active. They have huge earthquakes with some regularity. So it's a great concern there. And this is where Dr. Anwar and I have gotten to know each other quite well, working collaboratively on projects in the Philippines. Or Jakarta, another place in Indonesia, Southeast Asia, where the seismicity is very high, and they're building very tall buildings. So regionally, there's quite an important discussion that needs to be happening here, and engineers kind of increasing their capabilities in dealing with seismic design for tall buildings. A little bit of a history lesson then. I mentioned I started doing performance-based design about 22 years ago, and here's a little bit of a timeline. Starting in 1996, in this bar chart, this represents the numbers of buildings our company has designed over those last few years. The first one started was actually in the Philippines. This was in 1995. Actually, it says 1998. That's when the building was completed. We actually started the design in 1995. Asian Star Building was the name. It's in Alabama, outside of Manila. And it was the first time that we tried to implement what then we call displacement-based design. Ultimately, it became performance-based design, but this is the very first one that I'm aware of that kind of followed this methodology. And so from there, we started doing a number of buildings. The first one in the US was a fairly modest scale building outside of Seattle in Bellevue, Washington. And then we decided to scale it up, and these two towers in the Philippines, Pacific Plaza Towers, were done in the late 90s. And that this was really kind of the first adventure into fairly tall buildings where we were using performance-based design. Around that time, a number of groups on the west coast of the US started to gain interest in this approach, in this methodology. And in Los Angeles, the Los Angeles Tall Building Structural Design Council put together this guideline that the initial edition was in 2005. So now we're talking 12 years ago or so that this was published for the first time. And that was trying to give engineers some guidance as to how to go about performance-based design, at least in the Los Angeles setting. About that same time, we were designing this building, the first one for our company in California, a project now called the Infinity, the 240-story residential towers. And this project went through an extraordinary amount of scrutiny by the local engineering community. We did our design, but there was a peer review panel appointed that was comprised of 4 persons, very, very top of the industry persons, and in fact, one of those persons being, guess who? Professor Bertero, a professor from graduate school. And we were going through various review meetings, and he was asking me these very, very hard questions, and I was very frustrated because I was having a hard time answering his very hard questions. And at one point, I said to him, Professor Bertero, this is exactly what you taught me to do in your class. I'm just doing my homework and turning it in. And at that, he smiled, and then he was much more friendly. The poster child, I suppose, for performance-based design for the last 10 years or so has been this building, London Hill. And not only because it was a very tall building with a central concrete core, but it also had an outrigger system you can see here in this diagram. That had a series of buckling restraint braces used as outriggers. And so, in terms of the prescriptive language of the code, it was an undefined system. Not only were we going to design a very tall building in San Francisco in a high seismic zone, but we were using a system that wasn't described in the code at all. And so how would you go about designing this? And so once again, this building went through a lot of scrutiny, peer review, but it became kind of the poster child. It's on the cover of many of the guides and documents about performance-based design. On the heels of that building, the city of San Francisco wrote a guide. So if you're practicing in San Francisco, this kind of lays the rules of engagement. It was written by the Structural Engineers Association in Northern California. The Council on Tall Buildings and Urban Habitat published a guideline in 2008 attempting to introduce the international community to this methodology. And then, I think you're probably, many of you familiar with the peer TBI guideline, which has served really to guide the industry since 2010. All of these documents, to one degree or another, I've had a hand in writing, and still writing them. I have a few versions down here. Subsequent to those buildings, the buildings seem to get taller and more ambitious, and time has marched on, and we've done more and more and more tall buildings. And most recently, building in San Francisco that has a mega brace system on the outside. There's no concrete core in this building at all. It's a mega brace system. And all of these buildings in downtown San Francisco, for instance, have been designed and built using performance-based design in the last 10 years. So it's very prolific. Most recently, this is the Peer TBI Guidelines 2.0. So for those of you that are practitioners and are playing with performance-based design, you'll know that this document is already superseded. There is Peer 2.01, 2.02, and 2.03. And you'll notice 2.03 has a clip. Now you can get a copy of this on the internet. You can download it for free. It doesn't cost any money, it's free. But the reason it has a clip is we're still rating it. We're still fixing it. There's a couple of things inside of this document that aren't quite right yet. And like I mentioned in my opening remarks, this is an evolving practice, performance-based design. And so as you begin to use this document, 2.03, you should know that there is indeed going to be at least 2.04, because I'm working on it right now. Specifically, what is not quite right in this document is how we're intending to deal with the impact of vertical ground motion. And so specifically in that document, when you get into the details of it, and you're starting to look at what we describe as force-controlled elements, and you're assessing the demand on force-controlled elements, the equations that are in that particular version, 2.03, are too conservative. And we're studying right now at UCLA and at Cal Berkeley how to modify those equations to make them less conservative. How that's going to turn out, I can't say yet because it's still being researched. But we know that the factors are too conservative and we're going to throttle back on them. Maybe in a few months' time, you'll know what those are when I do. Also, this last week, I was in Sydney at the Council on Tall Buildings conference, and there's this document, which is the now 2017 version of the Council on Tall Buildings and Urban Habitats Performance-Based Design Guidelines. What's the two aspects of this guide that I think are useful for practitioners? One is it gives a good overview of the various topics and items to be thinking about, but most usefully, it gives 4 example designs in the back. There's 4 different buildings, 1 in Los Angeles, 2 in San Francisco, and 1 in Seattle. And the analytical approach and the results of some of the analysis are presented in the back of this guide. So it's a useful reference as you begin to start doing your own performance-based design. All right, so let's talk a little bit about technical issues. I just want to highlight a few that are important. The ones over the years that we've found in our own practice and continue to see as we go around the world: ground shaping, and then we'll talk about computer models and various demands. Ground shaping in particular, as we go from city to city, site to site, country to country, we continue to struggle with getting, shall we say, confident assessments of the actual seismic hazard at a given site. In San Francisco, there's a fair body of knowledge. There's a lot of very skilled practitioners, and so our confidence there is fairly high. But when we go to, say, Jakarta, where the seismicity is very high, the data that's available from actual measured earthquakes in Indonesia, the database is very small. And so our confidence level in being able to define the actual ground shaking hazard is not as high as we would like. And this needs to be taken into account with some engineering judgment as you progress your design, that if you have a high degree of confidence in the ground motion definition, or I'm a little suspect of what it is. And this is also only engineering judgment. There's no science here. You just have to understand why you have very, very powerful analytical tools, doing nonlinear response history analysis, doing response spectrum analysis, and so you have these very, very powerful numerical tools. The old saying goes, right? Garbage in, garbage out. And so the input ground motions and their definition is very, very critical to the end design and answer, and understanding them and getting, shall we say, way down in the weeds with the experts on the input ground motions is very, very important. Today, what we're doing mostly for our tall buildings is something that's called a scenario spectrum approach, or some people call it CMS, conditional mean spectrum. And that is we're defining suites of ground motion type history records for various target periods that a building might have. Because we've learned through our work over the years that tall buildings in particular don't generally respond in the first mode response, meaning they don't generally just sway back and forth like perhaps they do in the wind, but the response is much more dynamically complex. And many times it's the second or third or fourth mode of vibration that actually drives the demands of the building. And because of that, what we want to do is define a series of time history records, some driving ground motions, that target that critical period. So in this simple example, if this is the overall response spectrum, here you can see the blue line would be indicative of trying to target ground motions that are at a much shorter period, which might be the third or fourth mode. And when you get there is high accelerations driving that mode of acceleration, where out in the longer periods, first mode period, the demands are actually less. But by contrast, the first mode response might have a very long period, but that earthquake has a very low amplitude demands in the short period range. And so recognizing that there are different earthquakes and different ground motions that will drive different response of the building is very important. So commonly today, we'll define at least 2 target building periods, long period and short period, and for each of those target periods, we'll define 11 suites or 11 sets of ground motions. So in all total, 22 different ground motions, 11 at the long period and 11 at the short period. And that's pretty much our common practice these days. Of course, a computer model, an analytical model that we build is very important. The one thing that we've learned through the years on computer modeling is that calibrating your computer modeling techniques, your assumptions of how you build your model against actual laboratory testing is very important. For example, in our practice, we know that when we build our nonlinear response history analysis models, because of our modeling techniques, we use Perform 3D as our work engine for nonlinear response history analysis. We know with our modeling techniques that we fairly reasonably predict tensile strain in the rebar pretty accurately. So on the tension side, we're pretty confident, and this has been calibrated against laboratory testing. But on the compression side, we know we underpredict compressive strains. We underpredict compressive strains by upwards of a factor of 2. Now, that doesn't say our model is wrong. It just says from a calibration point of view, when we see the results of our model, we know that on the tension side, we're in pretty good shape. On the compression side, we're under-predicting strain. So that will cause us to make design decisions in a certain way. The whole point of that story is that I encourage you to test your own modeling techniques against laboratory testing of shear walls or moment frames or columns or what have you, to test how your resulting analytical results stack up against what's tested in the lab. So you can properly calibrate your model or at least your assessment of the output. It's very important. One thing that you see, these plots here now talk about, this is the nonlinear response of the building. This is the moment, or this is the height of the building and the bending moment in the building. This is the height of the building and the bending moment in the building. You see in this particular building, this big valley right here. And this is not uncommon. This is a higher mode effect in the building, driving the overturning moment in this particular building because of its geometry and the seismicity of the site. And what's the end result of this, which is interesting, right? If you think about it, that overturning moment there, due to that actual earthquake nonlinear response history analysis, is almost equal to the base moment. So in the classical sense of capacity-based design, where you think about a shear wall as a cantilever and the plastic hinge forming at the base, in this case, there is at least 2 plastic hinges, maybe, depending on how you choose to design and reinforce the building. But nonetheless, here, that moment is equally as high as that moment. But here, the gravity load on the wall is maybe 2/3 of the gravity load here, resulting in the reinforcing steel here that's required is actually greater than reinforcing steel at the base of the building. From a kind of classical engineering point of view, seems odd that I have less reinforcing steel at the base, more reinforcing steel, in this case, in this building, about 1/3 of the height, and then diminishing above that. But that's because of this combination of flexural demand and the axial load. So you end up with some interesting results that you need to digest and understand. And you can still force the plastic hinge here if you like, so long as you reinforce this properly. Yeah, it's not showing up too well. So this diagram, it's hard to read. I realize that what you're looking at here is the height of the building, and this is the shear at the base. And the yellow line is, in this particular building, the code prescriptive shear. So if you're going to do a prescriptive design of the building with the code factors, that's what you designed for shear-wise. The red line in this particular building is the wind loading, code prescriptive wind loading, and the black line is the result of the nonlinear response history analysis. And you can see there's a factor here. You can't read these numbers, but that's 5,000, that's 15,000. Doesn't matter to me, it's a factor of 3. But the actual shear demands on the building, on the wall in this case, are about 3 times what the code would otherwise require. That's not uncommon. I'd say that's typical. In most of our buildings, we believe that the code undershoots the demand for shear on shear walls by a factor of 2.5 to 3. This is being corrected as we speak. It's making its way through the committee process in the US, through ASCE7, through ACI, and I think in a few years' time, what you'll see in the code are some amplification factors. So if you choose to continue to do prescriptive design, you'll find in a few years' time that you must amplify the shear demands by some factor that's yet to be agreed upon. But if you do nonlinear response history analysis today, you see this result, and this is pretty common. All right, lots of watching. Let's move on. All right, so what we're going to see here, maybe? No. Is there a way you can launch this from there? This is an animation, and perhaps we won't animate it. Or maybe from here. Yeah. Can we hit the launch button? So what you're going to see here is, of course, up on the upper left, here's the ground motion. Earthquake ground motion. This chart is going to be just a stick model of a displaced shape. Here you're going to see the moment plot, and here you're going to see the shear plot with time, if it will run. Now run. Okay, we'll move on. All right, so what you would have seen, if the animation would have been successful, is that the deformation of the building isn't a first mode response. It doesn't sway back and forth like this. In fact, until the ground has stopped shaking. What you'd see otherwise is the building starts to whip like this, kind of like a snake, right? And that's the input energy of the ground shaking, making its way up the building. And so the building gets into a second and third mode response very quickly. And in fact, it doesn't even get to that point until the ground motion is well into the peak response. And I use an analogy, I say, a building responds to an earthquake a lot like my teenage son responds on Saturday morning. He's sleeping soundly in his bed, very peacefully, and I go in and I go to wake him up. I shake him, I shake him again, I shake him harder. Finally, it's, he wakes up slowly. And then after the shaking and finally waking up, he finally comes to. This is exactly how a tall building responds. That the ground starts shaking, and initially the tall building looks, what? What happened? And it's only after a bit of time that the building actually wakes up and starts to respond to that ground shaking. And after the shaking's over, the building actually starts to sway in first mode. And we see this time and time again with tall buildings. All right, some complications, very simple things to be aware of and careful with. So oftentimes a building has some kind of a setback in it, whether it be a geometric setback of architecture or a mass or stiffness setback in the structure. In this case, it has both. And when those things happen, right, complicated things begin to happen with the building performance. In this particular building, what I'd expect to have happen is right here in this location will be the peak demands. The peak flexural demands, the peak shear demands will all happen right there. Not at the base, right there. And so expecting those kinds of results, preparing for those kinds of results, and then when you see them analytically, not being afraid of them, is something to be aware of. Offsets in building structure, you can see here where the building starts in its top as maybe some kind of a core brace the building, and then that bracing breaks up and transfers over here. This is not uncommon, but what it does is put extraordinary demands on the diaphragm to transfer that shear force. And so properly modeling that diaphragm and considering the effects of the stiffness of that diaphragm are really important. Multiple towers on a common base is a very complex problem, and one that I'm not sure that we have all of the answers to just yet. Happens quite a bit all around the world where you'll have multiple towers sitting on a common substructure or a common podium structure. And how do those two towers interact? And how does their interaction affect the design of the podium and the podium diaphragm? Very, very complicated problem if there's no joint for that. Grade level diaphragm force is what we'll call a backstay effect. In other words, as the tower comes down and comes to the ground, and say there's a basement that's 2 or 3 or 4 levels deep, that ground level acts as a prop. And so what you have is really, very simply in this diagram, a prop cantilever. There's the ground level, the foundation prop, there's the ground level prop, and then the cantilever. This force can be huge. It can be 2 or 3 or 4 times the base shear of the tower, depending on the geometry and the conditions of the site. So understanding and expecting that backstay force to be present and then designing for it is very important. Oftentimes what happens is this grade level diaphragm needs to become very, very thick and very heavily reinforced in order to manage that force. Another topic that is seeing a lot of interest, a lot of research, and a lot of uncertainty right now is the embedment effects or soil structure interaction effects of the tower. To date, I think most of us in the practicing world assume that the tower goes down to its foundation and it has some pin supports, vertically fixed, translationally fixed, rotationally free, but don't consider much in the way of the embedment effect in the surrounding soil. The reason we don't do that is we don't know the answer. The stiffness properties of the surrounding soil are highly variable, and at best, from our geotechnical friends, a guess. And so practice has been to date ignoring all of that, and I'd say somewhat conservatively ignoring this kind of a model, but instead doing something more like this. That continues to be the practice, but there's growing interest in these much more sophisticated models. We do have the tools to allow us to technically, numerically model those effects, but we're not confident that we understand the results when we get the outcome. So I just put a big note of caution there. If you choose to try and assess soil structure interaction for your performance, seismic performance of your tower, be cautious and be very skeptical of the output. In fact, maybe best if you're going to do that, test the sensitivity of your analysis to your assumptions. And I think what you'll find is the sensitivity is very high. And small changes in your spring and damping assumptions for the below-grade soil can change the results wildly. So this should cause you some pause as an engineer and inform your decision-making. Offsets in geometry, in plan and section, transfer structures, these are all difficult problems that we face in a lot of buildings. Or in the classic case of an outrigger structure here, the notion of capacity design, if you have this outrigger like I showed in the One Lincoln Hill building, what is that outrigger's capability of actually delivering axial force to that column, and have you limited it in some way so that you don't fail the column in axial compression because that outrigger is somehow stronger than you expected it to be. If we go back to the One Lincoln Hill structure, that's why we chose to use buckling restrained braces for that building, because we knew and could control the upper bound strength of those parts in a very tight range. We knew the upper bound strength very specifically, where, as an example, if this here piece was an RC wall, what's your confidence level in being able to accurately predict the upper bound strength of that element that then drives the axial load in that column? Your confidence level will be lower just because there's a lot more variables involved. All right, so I'm going to talk a little bit about sales horsepower. This is in San Francisco. It's just now being completed. It's about 300 meters tall. It's just a little bit more than 300 meters. It's a concrete core wall building, and it has steel floor framing around it. It's an office building, 100% office, not mixed use. And what's unique about this building for our company, we started the design of this about 6 or 7 years ago, 6 years ago perhaps. And in that time, up until that moment, all of the buildings we had designed were categorized as something in the ASCE 7 context as a risk category 2 building, meaning it's an ordinary building, ordinary commercial building. This building, because of its size, because of the number of occupants that were going to be occupying this building, it was categorized by ASCE 7 as risk category 3, meaning it's more important. If you were looking at it in a prescriptive code context, what that would demand you do is take your code DVE seismic demands and multiply them by 1.25. So there's this 1.25 factor on code prescriptive seismic forces that go hand in hand with this category 3. For this building, we were not designing prescriptively, we were designing in a performance-based setting. So the question was, well, how do we implement that in a performance-based setting? Well, we're not going to really think about code prescriptive DVE forces. We're going to think about service level earthquake forces, SLE, and we're going to think about MCE forces, maximum considered earthquake demands. And within that setting, how do we implement acceptance criteria or demands that would be reflective of the code's outcome, the desired outcome of having a safer building because it's got greater risk, this category 3. I'm going to skip through that. So a little bit washed out. Sorry about that. So here's what we did. The thinking was this, that with design, there's two sides to the equation, right? There's the demand side, and there's the capacity side. So our ultimate objective was to make the building safer under the maximum considered earthquake. Safer than a standard building. Well, how much safer? And the code, by applying this 1.25 factor, was suggesting 25% greater. If you put it in probability of collapse and actual risk assessment, what is embedded in the ASCE 7 code is that for a risk category 2 building, a standard building, the probability of collapse under the MCE event is benchmarked at 10%. That's what we all, at least all of us in the ASCE 7 context, designed to today. That if you design prescriptively to ASCE 7, your building has a 10% chance of collapse under MCE. If you're at risk category 3, the code is looking at it saying that threshold of collapse should be reduced from 10% to say something like 6%, 7 to 6%. And so how do we achieve that if we're going to target a threshold against collapse around 6%? And so again, the idea was you can play with the demand side of the equation, or you can play with the capacity side of the equation. The demand side being the definition of the ground shaking. Commonly, ground shaking SLE event is a 43-year return period. The MCE event in most places in the US is a 2,500-year event. So we could tinker with those, make them bigger. Or we could play with the capacity side and instead say our threshold of acceptance for various pieces is lower. After a lot of thought and debate and discussion with our peer review panel, we chose the latter. We chose to stay with the definition of ground shaking as per normally defined, 43 years and 2,500 years. And the reason we chose that is that the seismologists have done a lot of work, and there's a lot of benchmarking, and there's a lot of knowledge built around those two thresholds. So the thought was, why tinker with that? Because if we tinker with that, we don't really know what we're doing. So we'll leave 43 years and 2,500 years. Instead, we'll go on the capacity side. And so, for example, if under a risk category 2 building, we would allow a peak seismic drift of 3% in a standard building, risk category 2 building. In this case, we would take 1 divided by 1.25 equals 0.8. 0.8 times 3%, 2.8%. So we apply a 0.8 reduction factor to all the acceptance thresholds, whether it be drift, strain, compressive strain, tensile strain, chord rotation on link beams, every acceptance criteria that we would normally assess for the building element performance and global building performance, we reduce the acceptance threshold by a factor of 0.8. And that's now, since we designed that building about 6 or 7 years ago, that's become the methodology that's accepted, at least on the western coast of the US. In Los Angeles, in San Francisco, in Seattle, that's become the way. All right, so here's another animation, and it's very subtle. It's to scale. This building's 300 meters tall. And so under the peak earthquake demand, it sways about 3 meters. Converting, it's 100 inches. So if we go back, I'm going to go back once this animation stops, so we can do that. Yeah, all right. So I'm going to advance it again, and we'll look at it. So you'll see the ground motion across the upper right. You'll see the very simplified model of the building. And 2 things to pay attention to. Number 1 is, it is to scale, so the motions look very small. The building response looks very small, but recognize it's moving 3 meters this way, 3 meters that way, right? So to put it in context, 1, 2, 3, I'm here. 1, 2, 3, 4, 5, 6, I'm here. And it took me about 6 seconds to get from there to there in the earthquake. That's how much motion is happening at the top of that building. Note that as the ground motion starts shaking, that you'll see again this wiggle in the building. It doesn't really sway, it wiggles. Only after the ground motion is stopped will you start to see the building sway. So watch carefully. It's very subtle. So the ground's just beginning to shake, and now the ground motion is going to start. There it goes. You can see it wiggling a little. You can see the snake there now. It's got a big bend in the middle. And it's still kind of wiggling around a bit. And now the earthquake's going to stop. The ground motion is nearly done. And lo and behold, there goes the first node. And it's not until the ground motion has already ended, essentially, that the tower actually starts swaying in the first node. And at that time, the amplitude of sway is fairly large, but the shear demands in the building are pretty small. This is the same building. This is a strain plot over the height of the building. So what you're looking at is that same Salesforce tower. This is the height of the building. Again, this is a core wall building, central concrete core. The green dots represent compressive strain in the core wall, and the purple dots represent tensile strain in the core wall. So a couple things you'll see. Number 1, it's very constant over the height. Wow, we're very happy because it's a very well-proportioned building. We're compressing strains because we're varying wall thickness and concrete strength and what have you over the height. The compressive strains are pretty consistent and within a very tight band over the height. And lo and behold, here you can see that threshold, that's 0.003. In other words, that dashed line is where you might start to worry about compressive strains as it relates to confining the concrete. So the compressive strains in this building are very, very modest. The purple dots represent the tensile strains, and this line represents right there, that dash line represents the yield point of the reinforcement steel. So once again, this building, nothing's yielding, nothing's yielding, nothing's yielding. Oh, lo and behold, 750 feet in the air, 220 meters, 230 meters in the air, we finally get some yielding in the building. What's going on here? What's going on there is the core wall was going up, going up, going up, going up, and now some of the elevators dropped off and the core wall got smaller. So there was a physical geometric setback in the core in the building, created a strain concentration, and so the plastic hinge, if you will, happens right there. It doesn't happen at the base of the building. And so our reinforcing steel and our detailing needs to recognize this, so there's more rebar and more detailing happening in that location at the setback than is happening at the base. Not uncommon, it doesn't happen in that building. These are the shear and overturning moments. Here we didn't see a lot of higher load effect. This building was actually, in terms of the actual physical, when you put all of the kind of boundary conditions or bounding of the solutions, or the overturning moments and the shears were pretty distributed well over the height. Here's the drift plots for that same building, and you can see here's where that offset in the building's core was. The drift is going up pretty straight, pretty straight, pretty straight, and right there we're going to be kink. That's because the stiffness of the building changed radically in that location. And lastly, coupling beam rotations. The last thing I think I want to talk about briefly is kind of where I started. And where I started was that I've been working on this for 25 years or more. I graduated from Berkeley in '85, so that's 32 years. And with each and every building, we learn something. And each and every building, we get better and smarter and discover things we didn't know. So we're constantly advancing our practice. And the thing we've learned along that journey is it's really, really important, if you're going to attempt to do this, to engage with some peer reviewers, one or more, who have the experience and knowledge and background to help you get better. I can tell you from our side, we've gotten to work with very, very brilliant people all around the world who've reviewed our work and asked us hard questions and demanded that we come up with an explanation or an answer. And that's made us better. And it continues to make us better. So if you embark upon a performance-based seismic design, which I encourage you to do because I think it's the only way to do it properly, don't work in a vacuum. Reach out to colleagues. Insist with your client that your work be peer-reviewed. Find someone who's experienced and knowledgeable in the subject and have them look at your work to make it better. And through all of that, we'll all learn together and make it better. So here's an ongoing peer review. Each and every one of our projects for 25 years has been peer reviewed, and we're much, much better because of it. And I've peer reviewed 20 of Dr. Anwar's projects, and he's going to peer review one of mine now. So the shoe is on the other. So anyway, thank you very much. It's been my great honor and pleasure to be with you this afternoon. I think we're going to have a discussion session a little bit later. But I'll look forward to speaking with you all in more detail. Thank you.